Welcome to class today. Are we ready to do some math? Miss Evans, it's almost summer. Can we just sit and tweet about our summer plans? Do we have to do math? But we have to. We only have a few more times in math class together before the summer. I'm gonna miss all my math buddies. I know you've all done such great work this year. I'm so proud of you all. Fabulous students.
Yes, let's get to mathin'!
Math it up! Missy, are we still dealing with rational expressions? Woo, 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 woo. Woo, woo. Yes, good memory, Drew. And today we're going to look at graphs of rational functions. Awesome. Ooh, that sounds juicy. Like some OJ over here. Wait, I'll have some OJ for the juicy math. Nice. Woo! Alright, so the definition of a rational function is when you have one polynomial, p of x, divided by another polynomial, q of x. Okay, and we know q of x can never equal 0 because then we'd be divided by a 0. So now let's look at a couple examples of rational function graphs using the power of technology. Bam! Pow! Kazam! I am a math wizard! Hey! Miss Evans, those are pretty complicated. Are we gonna have to graph those? Not today, Nikki. We're just gonna look at a couple of graphing characteristics so we can start to analyze these graphs. I agree, they are pretty crazy graphs. Let's first start talking about our domain restrictions. What if I wrote this? Let me grab my notes. On the board. X squared plus 3x plus 2, numerator, over x squared plus x minus 12. How would we find our domain restrictions here? Well, our restrictions are the denominator can't ever be 0. So how we find those restrictions are we factor the denominator and then we set those factors equal to 0 because we know they can't ever be 0. Denominator, duh. So that's how we find the restrictions. Couldn't have said it better myself, Broy. Alright, so let's factor the denominator. Oh, Missy, let me factor. I'm the factoring king. Alright, two numbers that multiply to give me negative 12, add to give me a positive 1. Let's see. Positive 4 and negative 3. X plus 4 times x minus 3. X plus 4 times x minus 3. X plus 4 times x minus 3.
Yes, so then the restrictions would be negative 4 and 3, since that would make the denominator 0!
Hey, would those be the vertical asymptotes? Woo, woo. Nice. Exactly. Whatever the domain restrictions are, those are our vertical asymptotes. Great job. Let's look at this specific example. What would our vertical asymptotes be here, fellow mathematicians? So I think you would set each binomial factor of the denominator equal to 0 and find your restrictions. So in this case, our vertical asymptotes would be x equals 7 and x equals negative 5. What, did I swallow a math textbook? Did you hear all that math vocab, Miss Evans? What? I'm like Einstein over here. What? Awesome, Petunia, you are correct. Our vertical asymptotes would be x equals 7 and x equals negative 5. Well done.
Miss Evans, I have a question. Remember when we were simplifying rational expressions and we canceled that binomial factor on the top and on the bottom? It went away, but it still counted towards our restrictions. Well, what happens then? Is it an asymptote? What happens?
Walter, that is such a good question! I need to know this now, Missy, what is it? We are mind twins! Exactly, so what happens if we have a restriction that cancels? So in this case, the x minus 1 binomial is canceled, and we're just left with 2x plus 3. Well, what type of a function is that?
Isn't that just a line, Miss Evans? Lines don't have asymptotes, so what's the deal? Weird.
You are so right, Bethany. So what happens is we graph this graph, but there will be a hole in our graph at x equals 1. Whoa! Graphs have holes? That is awesome! Woo! Walking on my graph and there is a hole. Fell in and stubbed my toe. Holes are great, holes on graphs. La 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 la, math, math, math.
So how would we draw that? Just a line with a hole?
Exactly! It is just like it sounds. We know that x equals 1 cannot be in our domain, so we draw a line, and when we get to x equals 1, draw a hole, and then just continue our line.
Wow, that's so neato, Miss Evans.
It's like a street with a pothole. Arg! Fix those potholes, you graph!
Okay, so we talked about our vertical asymptotes and our holes, but aren't there horizontal asymptotes we haven't talked about yet?
Great question, Walter. So to determine horizontal asymptotes, we're going to look at the degree of the numerator and the degree of the denominator. Do you guys remember what I mean when I say degree in terms of mathematics degree? You know, like, ooh, the summer degree is hot outside. Degree, do we remember?
Isn't it the highest exponent power in a polynomial or something like that?
Exactly. So the first horizontal asymptote we're going to look at is y equals 0. So if you have an asymptote of y equals 0, the degree of your numerator is going to be less than the degree of your denominator. So for example, this one, the numerator has a degree of 1, the denominator has a degree of 3, so we have our horizontal asymptote at y equals 0. Nice! Okay, that seems easy enough, but what happens when the degrees are the same? What's the horizontal asymptote then? Great question! So if the degrees in the numerator and the denominator are the same, to find the horizontal asymptote, just take the leading coefficient of the numerator divided by the leading coefficient of the denominator. In this case, it would be 6 divided by 2, which is 3! It's 3! Woo! Wow! Miss Evans, we are rocking this! This seems pretty challenging, but we are super math geniuses! Woo!
So what about a higher degree in the numerator? What happens then, Miss Evans?
Ooh, yes, intriguing. What happens, Missy? I gotta know now. I'm so excited. So that's the last case. If the degree of the numerator is higher than the degree of the denominator, there is no horizontal asymptote. Get out of here, horizontal asymptote. You don't belong on this graph. So no horizontal asymptote in that case.
That's a lot of information we just learned. Let's all recap what we learned. Okay, so if the horizontal asymptote is y equals 0, then we know that the numerator's degree is less than the denominator's degree.
Got this. Case 2. If the numerator degree and the denominator degree are the same, the asymptote is the leading coefficient of the numerator divided by the leading coefficient of the denominator. Woo! Wow, I'm great! Killing over here, Miss Evans! Woo!
I want to do the third case. That's when there is no horizontal asymptote and the degree of the numerator is greater than the degree of the denominator. All 3 cases.
Awesome job! You see, class, that wasn't so bad. If this is the kind of math we're doing, I could do this all summer long with ice cream on top. I'm so excited for ice cream season. Anyone else? No, just me? All right. Alright, let's try analyzing a specific function. What would my asymptotes be here? Or are there any at all? You try it. Well, the numerator degree is greater than the denominator degree, so there isn't a horizontal asymptote. Neato! Good eye, Nikki.
So I factored the denominator. See, nothing cancels, so no holes. And I just got a restriction of x equals 1. So wouldn't it be a vertical asymptote at x equals 1 to 7s?
Yeah, that sounds super mathy.
Oh man, I'm gonna miss math so much over this summer. I don't want math to ever end!
Don't worry, Walter. You'll always be in math class in here. Your heart.
Wait.
Come on, Bethany. I know you love math. Admit it. You love it. You love math.
Fine, I like it all right. I mean, I'm pretty good at it. It's kind of fun. I like math, all right?
Pretty fun.
1, 2, 3. 1, 2, 3.
Oh yeah, what's summer, guys? You're almost there. Woo, math party.
All right.
Burn. Yeah. Woo.
Mashed potato. Do the alligator. Put your hand on your hips, yeah. Let your backbone slip.
Have a good summer, everyone. Wanna join my summer math club? Oh yeah! Oh yeah! Oh yeah! Oh yeah! Oh, Ricky! Woo!
Somebody help me say it one time.
Oh, yeah! It's gonna make a tune, Ooh, hi, what's up? Woo, woo, woo! I'm just kidding, man, I'm so quirky!
You know I feel all right.
Honestly, this is the summer, straight at you. Oh, good times in math class.